talk about Unit 5, Topic 4. I apologize for this coming out a little bit late. When I recorded the session yesterday during our Google Meet, when I logged out, the video was not there, so had a little technical issue as per usual. So we're going to move on. Let's talk a little bit about the ocean and the salt or the salinity of the ocean. The ocean is approximately and very close to 3.5% salt. Anywhere you go in the ocean, that's going to be the salinity content or the salt content is 3.5%. Because if you look at the globe, you're going to see that whether you're looking at the Pacific, Atlantic, Indian, Arctic oceans, all of those oceans are connected. And it's not like there are land masses that keep those oceans from mixing. So over time and with the ocean currents, all of the ocean water salinity is relatively the same. So the question is, well, why do we have salt in our ocean? Why do we not have salts in our freshwater lakes, but why do we have them in the oceans? And the answer is actually fairly simple. So the ocean is continually being fed salts from rivers and so on and so forth. And right now you're probably saying, well, rivers aren't salty. That is true. However, as the water runs across the rocks of the rivers and across the land, it's going to pick up substances. It picks up substances, and of course, the water, we know its eventual resting point or final destination is the ocean. It's going to run into the ocean. Now we have to think about the water cycle a little bit to explain how this works, okay? Because we know that when water evaporates, whether it be salt water, water with chemicals, colorings, whatever, when it evaporates, the only thing that goes is water. So anything that was in the water or dissolved into the water, when it evaporates, is left behind. So in the ocean, all of the substances that were carried there are left behind. And the water evaporates out and, of course, goes into the clouds. Those clouds rain down into the mountains and on land and in the ocean, but, of course, over land as well. And that process repeats. So the precipitation is going to run across those rocks. It's going to continue to pick up. It's going to continue to pick up different substances. So you can see here from this chart that 3.5% of the ocean is salt. Sodium chloride is the chemical name for salt. You can see it's by far the largest proportion of a substance, a dissolved substance in the ocean. You can see there's sulfates, calcium, potassium, but those make up a very small percentage of the ocean in comparison to salt. So the question is, if the ocean is continually being fed salts, why isn't it getting any saltier? So I did a little bit of research because the textbook doesn't really explain that too much. And the best answer that I could find is that it is changing. However, it is such a minimal change that it's almost immeasurable. Remember, the Earth is 64 billion years old, so the ocean has continued to accrue these salts over those 64 billion years. So from year to year, there's virtually not going to be any change. And some might even argue that the Earth is getting less salty because of glaciers melting and polar caps melting and so on and so forth because of global climate change. Let's move on. Let's talk about the ocean floor. The ocean floor is divided into two main regions. One called the continental margin, which is composed of the continental shelf and the continental slope, which you can see right here. And then beyond that, we have the abyssal plain, the dark abyss, which is the deepest parts of the ocean. Okay, so if you imagine right over here in this area is your land, you walk out onto the beach and you have this general gradual slope, and then boom, there's this steep drop off. That steep drop off is your continental slope. And then you have a flat, deep area, which is just layers and layers of sediment that have been deposited there over years. And that is called the abyssal plain. It is the dark abyss. All right, so waves. So in Unit 3, we talked about electromagnetic waves. We talked about the parts of the wave, and we use the same language and terminology to explain ocean waves. So the top part of the wave is called your crest, the bottom is your trough. The distance from crest to crest is your wavelength, and you measure your wave height from the resting point of the water to the top of the crest. So it's really the same. So where do waves come from? The simple answer is winds. If you go to the lake and it's a calm day, you're going to notice there's not really any ripples. It might be glassy water. If you go to the lake on a windy day, there's going to be waves. Well, ocean waves are the same. They come from winds. And the normal winds that exist on the ocean on a day-to-day basis will create waves that are approximately 2 to 5 meters in height. However, hurricane winds can create waves that are 30 meters high. Wouldn't want to be around those ones. Other ways that waves could be formed, earthquakes. When the tectonic plates of the earth, when they collide, they're going to create tremors and earthquakes. That's going to obviously create movement of the water. Let's go on to breaking waves and how these break. So, as we talked about, waves being created by winds, principally or mostly by winds. You can see these little wind waves are coming in. As we get closer to the shore, you're going to notice that the height of the wave begins to get greater. It gets shorter, the wavelength is shorter, but the height is greater. Then as these waves get closer, the bottom of the wave begins to drag along the surface here, or I guess you could call it the shore. And as it drags along, what happens with the increased height of the wave begins to lean forward, and then it begins to topple forward. And that's when the wave breaks. And we call a wave that is breaking, we call it a breaker. All right, so you'll notice that the ocean shoreline does not look the same everywhere. Everywhere you look along the ocean, it's not going to be a beautiful sandy beach. In fact, if we just look further down this beach, we're going to run into a situation where we have all of these high, steep cliffs. Now, obviously, we have the same ocean area, regional, like the same region of the ocean here. The same waves are going to be coming in and crashing down on here, as are going to be crashing down on here. So what is it that caused the cliffs to form here versus the beach to form here? Because obviously with the waves crashing down, that's going to be that's erosion that's taking place, right? Every time that water smacks against the cliff, it's going to maybe break away a little bit of sediment. Same deal, if the waves are crashing down on the sand, it's going to rub the particles of sand together, and it's going to break them down over time and make the particles of sand really fine, and so on and so forth. So why a beach here and why a cliff here? And the answer is actually fairly simple. It all has to do with the slope. Okay, so if you have a nice gentle slope, like you would with a beach, right? So there's like a very gradual drop off. The waves begin to crash down, and that sand is going to, like I said before, it's going to rub against each other. It's going to break itself down into fine particles of sand. But as it does that, the sand, because of the gentle slope, it's going to basically be redeposited more or less in the same location. So crash, sand rubs against each other, there's some erosion, and then the wave washes back out. But what does the wave leave? The wave leaves the same particles of sand. However, over time, over millions of years, those particles of sand become finer due to erosion. So that's with a gentle slope. If we talk about the cliffs and they have a very steep slope, well, it's going to crash against those cliffs, against that steeper slope in that area there. Then the particles wash out, but do the particles get left in that same area on a gentle slope? The answer is no. Those particles are going to go redeposit in the ocean, and then they're going to get carried out to sea, deep back out to sea. And so it is going to create a situation where you have a steep cliff that begins to be formed over time. So, in the world we live in now, almost every shoreline especially in climates that are warm, nice climates, pretty much every shoreline is occupied by people. And those people or those public facilities want to be preserved, because beaches change shape over time. They just do naturally because of the action of waves. So if you have a public beach and you want to preserve it, breakwaters, jetties, and groins are constructed often to basically reduce the impact of the waves and the erosion caused by the waves. So we have a couple pictures here. We have what is called a jetty and what is called a groin. Now, a jetty is a wall that extends from the land into the ocean, and it's used to prevent sand from blocking the mouth of a river. And a groin is built at a right angle to the beach to prevent sand movement on the beach. So if you look at these two pictures here, which one is the jetty, which one is the groin? So as it says here, the jetty is the one that is used to prevent sand from blocking the mouth of a river. So right here is the only one where you can see a river flowing into the ocean. So they've constructed this jetty that juts out here. It's going to prevent this sand from coming in here and mucking up and blocking the edge of the river. Why is this important? Well, why can't the river? Because the river is going to find its way to the ocean. Well, as you can see, there's houses and other stuff that's right along the edge here. If you didn't have this jetty here and the sand began to block this river, well, the river is going to reroute itself and potentially right into the people's homes and so on and so forth. So that's why a jetty would be used there. And here we have a groin, and as I said before, a groin is built at a right angle to the beach, right? So here we have our beach, here we have our 90-degree angle or our right angle, and it's simply there to prevent the waves from doing too much, slowing down the waves so that they don't change the shape of the beach too significantly over time. Talking about tides, one of the main things that you need to remember is that the tide is really the main factor that influences tides is the pull of moon's gravity. I have two images here. We have what is called a spring tide here, and we have what is called a neap tide here. Now, notice these are not to scale. This light blue coloration represents the tides being pulled towards the moon, okay? So obviously, this is not to scale, because if it were, then this tide would be like several kilometers thick, like hundreds of kilometers thick. So it's not to scale, but it does show you that that water level raises towards the moon over here and on the opposite side as well. So notice with a spring tide, which is when the tides are at their greatest, the sun and the moon and the earth are all forming a straight line. Now, of course, we know the earth rotates, the position of the moon changes relative to the earth. And then we have a situation where we create a 90-degree angle. We have the sun, the earth, and the moon. Those are called our neap tides, and that's when the tidal movement is at its smallest. Let's talk a little bit about surface currents. Surface currents, they're influenced by three factors. And first of all, the uneven heating of the Earth's atmosphere is probably the greatest factor. Rotation of the Earth, and then of course the continents. These are all factors that influence surface currents. So surface currents meaning the winds pushing the water along into different areas and so on and so forth. So these winds are created by uneven heating. Now let me explain kind of how that works. So if you think about the equator, obviously along the equator you're going to have more radiation from the sun, more heat from the sun in those areas than if you were to go further up north towards the pole or further south towards the South Pole. Okay, so when you have cold winds mixing with warmer winds because of the amount of heat from the sun, it's going to create a swirling effect, right? Because the density of the air is going to be different. They're going to be almost like diffusing across each other, across to the other side, and it creates these swirling winds. Well, the swirling winds push the water along and create currents. And we'll talk more about the impact of that in a bit. The rotation of the Earth also affects surface currents, and then continents. So continents act kind of like a windbreak. So if there's a big land mass there, it's going to obviously affect how currents flow, right? So if current hits the North American continent, for example, it's going to slow down and redirect its course. Okay, we'll come back to surface currents in a bit. Let's talk about ocean temperatures, because the ocean, and really any large body of water, it consists of three distinct layers. And when I say distinct, it means that it's not a gradual change, it's really kind of a sharp change. So at the very top, you have what is called the mixed layer, and that's obviously receive the most amount of sun's radiation. It also is going to be the warmest part of the ocean, okay? Except for in the winter time on a lake when it freezes over, and we'll explain that in a second here. Just below that, we have the thermocline, which is the area of greatest temperature decline. So it really drops off quickly in this area here, and then we get to a point where all of a sudden the temperature is a steady cold in the deep water area, and it will remain like -2 degrees Celsius year round, and it's always going to be really frigid, cold water. But there's a very sharp change from each one of these layers. I remember as a kid, I went down to Lake Powell, and it was hot, hot, hot all the time. And this mixed layer area of the water was super warm. It was like 85 to 90 degrees Celsius in summer. So if it's 40 degrees Celsius outside and you want to cool off and you jump into the ocean, or not the ocean, but you jump into that lake and it's warm, you don't really get an opportunity to cool off. What I discovered is that when I was floating in the water, my feet would get cold. I could feel a very sharp change from this top layer to this layer just beneath it. And so I would go down and I would hang out in the thermocline region, or the area of cooler temperatures, and I would just stay there as long as my breath would allow me in order to cool off, because it was a really significant change from here to here, and it was a very sharp change. It wasn't a gradual change. It was like warm and then all of a sudden cool. So question, why do you think the coldest water is lower down? Why is it lower down here? Well, someone yesterday during our meet said it's kind of like air, because warm air rises and cold air sinks, and that's actually fairly true, because what happens is we talk a little bit about density way back at the beginning of the school year, and we know that the density of cool air is actually greater than the density of warm air, which is why hot air balloons, that's why they work, is because you heat up the air's density gets less and less, and it creates enough lift for a hot air balloon to come off the ground. Well, to a lesser extent, water is the same way. The cooler the water, the greater the density, which means that the cool water is naturally going to sink lower, and the warmer water is going to rise up. So if you believe that the water is warmer near the top simply because it's getting sun's radiation, that's not the only reason. It's more because the density of water is less when it's warmer. Now, it doesn't have to be significantly different for there to be a separation of the waters. Another thing to keep in mind through all of this is if you go to a lake in the middle of the winter, you're definitely not going to find the warmest layer of water right at the top, because it's going to be frozen. Underneath that, yes. And then, of course, you're going to have your different divisions. But, of course, we know because the air cooler outside and exposure to fresh water, it's going to freeze up that top layer. And that top layer, even if it's frozen, it's going to be the coldest. It's not going to sink, because we know what happens to the ice when it freezes. When ice freezes, or when water freezes and becomes ice, it expands and therefore makes it less dense. And because of that density difference, that's why ice forms on the top of the water. All right, so let's talk a little bit about oceans and climate. So a couple things that I want you to understand about water. Water has the ability to hoard heat, I guess you could say, or in a way, it has a great thermal capacity. It holds the heat very well. So I have a couple of pictures here. This is actually a picture of the Flathead Valley. So it's really just a few hours, short driving hours away. And it's really not much further south than where we live whatsoever. But if you look at this vegetation right here, you're going to see, whoa, those are cherries. Those are like real deal cherries from an orchard. And you might be asking yourself, why can't we grow these here in southern Alberta? Well, you know that the Flathead Valley, for those of you who have ever been there, it's not along the coast of the ocean. However, this lake right here is called the Flathead Lake. It is a very large body of water. It's so large, in fact, that it actually doesn't freeze over in the winter because it holds its heat so well. As a result of it holding its heat, it actually moderates the temperature in that area, especially along the eastern shore of the Flathead Lake. It keeps it so that it doesn't get too extremely cold, which allows for these cherry trees to survive through the winter. If you were to take one of these same cherry trees and plant it in southern Alberta, some of our harsh cold temperatures would wipe it out and it would not survive the winter. Here's a picture of Juneau, Alaska, which is the capital of Alaska. Now, if you're familiar with U.S. geography, here we are down here in southern Alberta. Further up north, we have Juneau, Alaska. So here's the large state of Alaska, and you can see it kind of brings in this area here as well. Well, Juneau is quite a bit further north. So you would expect that the temperatures in Juneau, Alaska in the month of January are going to be really, really, really cold. Now, if I told you that actually we're colder here in southern Alberta than they are there in Juneau, Alaska, would you believe me? Well, if you don't believe me, let's look at this temperature chart here. So in Juneau, Alaska, let's look at the month of January. The average high temperature is 2 degrees Celsius. This is January. And the average low is -3 degrees Celsius. If we go over here, here's Lethbridge, which is representative of southern Alberta. The average high is lower. The average low is a lot lower than Juneau, Alaska. And so if you got anything by what I had said earlier about how the cherry trees don't die along the Flathead Lake, it's the same exact principle here. Juneau, Alaska is along the coast. So it's along the ocean, the Pacific Ocean there. And despite the waters being quite cold there along the Pacific Ocean, it still is, the temperatures of those waters are still going to be warmer than -1 or -12 degrees. And it's going to moderate the temperature even in a place like Juneau, Alaska and further north. Now, if you look at a month of July, which is typically the hottest month, you're going to see that -17 is the high, -11 is a low. Those are your average temperatures. If you look at Lethbridge or southern Alberta area, where we know our temperatures get a lot warmer than that in July, well, it's because not only does it moderate for extreme colds, it also moderates for extreme hots, which is why if you go to the most southern state in the United States, which is actually Hawaii, you're going to find that the average temperature there is about 25 degrees Celsius, maybe up to 30 degrees Celsius, 80 to 85 degrees Fahrenheit, which is a nice, comfortable temperature. If you were to go to a state that is not as far south, such as Arizona, you know it's far south because it does border Mexico, but if you go to a state like that in July, the temperatures are going to be like 40 degrees Celsius, sometimes even warmer than that. And the reason for that is Hawaii has an ocean to moderate the temperature and to keep things relatively comfortable temperature-wise, whereas Arizona is landlocked. There's no ocean or large body of water to keep temperatures cool, so you're going to have those extremely hot temperatures in areas like that. So this is our last slide, and this is another illustration of how currents affect climates. So if we look here, and this is not to scale because if it were, the Atlantic Ocean would be much wider than this and these land masses would look smaller in comparison to the Atlantic Ocean. But I digress. Right here we know this is the Hudson Bay. And if we go straight across the globe, we're going to find ourselves, this is England, okay? Now, if you think about the temperatures and the climate in the Hudson Bay, you're going to probably know, and if you don't, I'm telling you, the temperatures in the Hudson Bay area are very cold, right? You're basically up there in the Arctic, there in the Hudson Bay area. It's just icy all the time. It's cold. Nobody really wants to live up in that area because it's so dang cold. Everybody in Canada really congregates mostly along the 49th parallel or bordering the United States. Not too many people live much further north. And now the Hudson Bay, England, population-wise, you're going to know there's quite a few more people that live in England, right? It's a very populated country, yet it's as far north as Hudson Bay. Now, if you know anything about the weather in England, you know it's a very mild climate. It's not extremely warm, but it's not extremely cold either. So what is the difference? Well, the difference really, if we're going to compare the two, is that over in this area here, we have no real ocean currents coming in, so it's just going to have those frigid temperatures. You have a current off of northern Quebec here, which is the Labrador current, which is going to bring very, very cold conditions because it is a very cold water current. So those winds push those currents along here, making this climate far different from the climate right here, which is having this Gulf Stream current, which comes from the Caribbean, pushes across the Atlantic, and then it brings warmer water conditions to this area right here. So with this Gulf Stream, it's going to change the climate of England, making it much milder as far as the temperatures go. So that's really it. Hopefully you understand a little bit more about what the oceans are and how they affect the global climates. And I wish you the best of luck on your quiz. You can refer back to this screencast if you ever need any help. Good luck. We have one more week to go, and I wish you all the best. Take care.